Hi everyone, today we are going to finish up our discussion on Lewis structures. So, the first thing is that in all of our Lewis structures, we've been showing bonding between atoms. Sometimes it's the same atom, sometimes it's different atoms. But those bonds have all been the same type, which is a covalent bond. And how I want us to think about covalent bonds is that it is a sharing of electrons between what is often, and what will most often be the case in this class, two nonmetals. So all the Lewis structures that you've drawn have been showing bonds between two nonmetals. So how do covalent bonds look? Well, you can have single covalent bonds here, like I'm showing in blue. You can have, you guessed it, double covalent bonds, which I'm showing here in l'orange. And you can also have triple covalent bonds. And that's the types of covalent bonds that there are. Now, what we need to think about also is what is a polar bond. So we can have polar covalent bonds which occur, I don't know, is occur 2 R's? That doesn't look right. Or is it 1C, 2 R's? Occur, spelling, between two atoms which exhibit different electronegativities. So what that means is that you can have a polar covalent bond, and that will occur between two atoms that have different electronegativities. So as a counterexample, this bond between the two nitrogens is a non-polar covalent bond, because the difference in electronegativity, delta En, here is going to be equal to 0 because it's the same atom. In all of these other molecules that are drawn, we're going to have essentially all polar covalent bonds because there will be a difference in electronegativity. Now, obviously, that difference can be smaller or larger. It's not so important in this class that you're able to calculate a numerical value. It's more important to qualitatively understand the differences. So let's look at this first molecule, nitrogen and hydrogen. Anytime you have anything bound to nitrogen, oxygen, fluorine, chlorine, bromine, iodine, anytime you have something that's bound to these atoms that's not one of those atoms, it will be a pretty polar bond, right? So as an example here, we have hydrogen and nitrogen. This is a polar bond. It's quite polar, right? And we can sort of assign the degree of polarity and sort of further explain that by showing the partial charges. So I'm going to put a partial negative on the nitrogen and partial positives on the hydrogens. The reason for this is because nitrogen is more electronegative than hydrogen. That means that more electrons will be closer to the nitrogen. Okay? It is more electronegative. The nitrogen is more electronegative, which means that it wants those electrons closer to it a greater percentage of the time. Now let's look at the second molecule here. This is called aldehyde. So here you'll see that we have a carbon bound to an oxygen. So that is definitely going to be polar, right? Like I said, anytime you have an atom bound to one of these atoms, it's going to be a polar bond. So I'm going to put a partial negative by the oxygen and a partial positive by the carbon. That is because oxygen is more electronegative than carbon, is more electronegative than carbon, which means that, again, more electrons are going to be near the oxygen a greater percentage of the time. Now, you're thinking, okay, what about that carbon-hydrogen bond? Carbon-hydrogen bonds are generally considered non-polar, right? So we're not really interested in any carbon hydrogens, okay? If we look at this fluorine hydrogen, fluorine is way more electronegative than hydrogen, so I'll put the partial negative here, partial positive on the hydrogen. Remember that nitrogen bond, when you have a homodiatomic molecule like this, it is nonpolar because there is no difference in electronegativity. When we look at boron trichloride, again, you have an atom, boron, bound to one of these elements up here in this box, right, the chlorines. So here we have 3 polar bonds. So I'm going to put the negative, the partial negative charges by the chlorines and the partial positive charge by the boron. That is because chlorines are more electronegative than boron, and the electrons are going to want to be closer to the chlorines a greater percentage of the time. Here we have oxygens, right, which is one of those 6 elements up there, and then we have xenon, right? So this is a polar bond because it's an element bound to one of these guys up here. So take a second and try and put down where you think the partial positive and partial negative charges will go. Okay. Hopefully you said the partial negatives are by oxygen, the partial positive is by xenon. If we keep going, we can do this for all these. And really, you don't even have to put a partial positive by the phosphorus because it already has a positive charge, but fine, just for consistency. And then here, right, fluorine's more electronegative than sulfur, so it's definitely going to be polar. These are polar, 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 polar. Okay? So we were talking about polar covalent bonds, and we were assigning these partial charges. Now, whenever you have a polar bond, there also exists at the same time a dipole moment. You can show dipole moments by drawing a sort of arrow like this. The arrow points towards the partially negative atom. So the arrow is going to point towards the partially negative atom. So if we go back through, we can assign dipole moments to all of these atoms. So as an example here, we have 3 dipole moments pointing towards the nitrogen. We have 1 dipole moment pointing towards the oxygen, 1 towards the fluorine. No dipole moments here. We have 3 dipole moments pointing away from the boron, 3 dipole moments pointing away from the xenon, 4 dipole moments pointing towards each chlorine, and 4 dipole moments pointing towards the fluorines. Now, why are dipole moments important? Because we're going to use them to determine if an entire molecule, for example, is polar. So you can have polar bonds, but you can also have polar molecules. So the question is, the final question of this unit, is the molecule polar or is the molecule nonpolar? Right? Just because there are polar bonds in a molecule does not mean the whole thing is considered polar. So let's see. In order for a molecule to be polar, it must contain polar bonds and an asymmetric molecular geometry. If the molecular geometry is symmetric with respect to the central atom, it will be nonpolar. If molecular geometry is symmetric, the molecule will be non-polar. Okay? So I need to move all this stuff down some, just a little. Okay. So, right, this is trigonal pyramidal, right? And each one of the dipole moments are pointing up towards the nitrogen. So you can think about this as like an actual pyramid, and each one of those dipole moments is pointing up towards the nitrogen, which I'm going to highlight here in yellow. Now this is an asymmetric molecular geometry, so this molecule is polar, right? You can see, because really what's happening is, since all these dipole moments are pointing in the same direction, you can kind of add them up, right? What happens is, if they're in a symmetric molecule, they can cancel each other out. If they point away from each other, they cancel out. As an example, like this cancels each other out, right? Here you'll see that they do not point away from each other. They're all pointing in the same direction. Okay, for the second molecule, right, the dipole moment point towards the oxygen. There is no dipole moment opposing that. There's no dipole moments pointing in the opposite direction. So this one is a polar molecule, right? If there's only one dipole moment present in the molecule, it is polar, right? Here, we've got a dipole moment. There's only one dipole moment. There's nothing opposing it, right? There's no other dipole moment pointing in the opposite direction. So it too is polar. The whole molecule is polar, right? This is a non-polar molecule, right? Because it doesn't even have any polar covalent bonds in it. Boron trichloride. Now this is a classic example of a symmetric molecular geometry. This is trigonal planar, right? This is a symmetric molecular geometry. Each one of those dipole moments is going to point away from each other symmetrically. So you may not see it, but ultimately they all cancel out. So this is a non-polar molecule. Even though it has polar bonds in it, the whole molecule is nonpolar. Xenon trioxide has trigonal pyramidal geometry, right? We know trigonal pyramidal is a non-symmetric geometry with respect to that central atom, right? And so what this one looks like is we have all of our dipole moments pointing away from the xenon, which is highlighted here, right? So they're not opposing each other. They're all facing the same direction. So this is an example of, again, a polar molecule. Here we have a tetrahedral molecular geometry. This is considered a symmetric molecular geometry with respect to the central atom. So this would be considered non-polar because each one of those dipole moments is facing away. Now you know that tetrahedrons, right, are not actually flat. They kind of look like this, sort of like that, right? So all of these dipole moments are facing away from each other, and it may not be so clear, but they do all ultimately cancel out. Here we have a seesaw molecular geometry. This is asymmetric with respect to the central atom, so it is considered polar. Now look at this though. These two dipole moments, they cancel out. Cancel each other. It's like adding a negative number and a positive number, so they don't even affect the molecule. But then you have two dipole moments that are pointing in basically the same direction. So these two, they like add together, right, to give ultimately a polar molecule. So again, in order for a molecule to be polar, it must contain polar bonds and be of an asymmetric molecular geometry with respect to the central atom. So if we go through and look at our list, we'll say linear is symmetric, trigonal planar is symmetric. I'm going to copy that. Angular is, we'll say, antisymmetric. Tetrahedral. Tetrahedral is asymmetric. Trigonal pyramidal is antisymmetric. Angular, which we're really going to call bent here for water, is antisymmetric. I don't like angular, I like bent. Trigonal pyramidal, symmetric. Seesaw, antisymmetric. Am I spelling symmetric wrong? I don't know. T-shaped, very antisymmetric. Woohoo! Linear, you guessed it, symmetric. Octahedral, very symmetric. Square pyramidal, antisymmetric. Square planar, very symmetric. Okay, and what you can do is you can draw and look at these shapes and point the dipole moments either away from or towards the central atom, and you'll see that they ultimately end up being polar. As a final example, if we think about square pyramidal, for example, let's do BRF5. Right, so here we've got our sort of, well, those aren't really bonds, I don't want to confuse you. But the dipole moments point away from the bromine. So you're like, well, Mr. Hicks, all of these guys down here in red, they do cancel out ultimately, right? You'll see that this one is canceled out by this dipole moment and vice versa. This one's canceled out by this one. But there's one left over. There's one up here. This one is not canceled out. That's why we call it antisymmetric. That's why this molecule would be considered polar. In all of these antisymmetric cases here, if you draw the dipole moments, you'll see that one is either left uncanceled or several of them add together to give a net direction, to give a net dipole in a certain direction.